When we start thinking about the world in computational terms, there's a question of sort of what does that mean? People will say things like, if the world is computational, where's the computer that it's running on? This is a confusion. Models are a way of representing what the natural world does. They're not mechanistically what the natural world is doing. This is a deep rabbit hole, but let's go into it. Let's start off with physics. And, what is the physical world made of? We start back in antiquity, people arguing, is the universe discrete or continuous? We learn by the end of the 19th century that matter is discrete, kind of the realization that we've had in recent times, that's sort of the foundation of the things I've done, is that we can think of space as also discrete. And so we think, what's in the universe? What's the universe made of? Well, we think of it as a bunch of discrete atoms of space. They're not atoms in the sense of chemical atoms. They're atoms in the sense of being indivisible units. There are atoms of space, and the only thing one can say about the atoms of space are how they are related to each other. And we can represent that by a network where we say this atom of space is kind of connected, related to these other atoms of space. So we represent the whole universe just as a graph, a network. And we imagine that the universe and space and everything in it is just features of that network. What there ultimately is just this network that represents space and everything in it. Well, another question is, well, what does this network do? That might be in sort of technological terms, the data structure of the universe, but what now is the algorithm of the universe, so to speak? And for that, what we imagine is that this network, we look at little pieces of this network and we say there are a collection of rules that say whenever you see a little piece of network that looks like this, it gets rewritten to a piece of network that looks like that. And this just keeps on happening. And that process of the rewriting of the network, that is the progress of time. That is, the time is kind of corresponds to this progressive computational process of the rewriting of this network. And one thing one can ask is, well, what's the large-scale effect of that? If there are, 10 to the 400 of these atoms of space, and they're all getting rewritten in all these ways, what does that do in the aggregate? And sort of an analogous situation is what happens in a fluid, where we know what happens at the level of individual molecules colliding and bouncing off each other and so on. But then the question is, what is the aggregate effect of that when we look at zillions of molecules together? And we know in that case that what emerges is fluid mechanics. Well, in the case of these networks and atoms of space and so on, what seems to emerge is general relativity, the theory of gravity, Einstein's equations, and so on. That's the thing that is the aggregate effect of all these microscopic processes associated with the structure of this network. Well, then what happens is there are all these different sort of ways that the network can get rewritten, but there are all these different parts of the network that can be rewritten separately. There isn't sort of a single thread of history that says the network is in this form, and then in this form, and then in this form. There are lots of different possible threads of history that correspond to different possible orders in which these little pieces of rewriting can be done. And that possibility of all these different paths of history is what leads to quantum mechanics in our models. What's characteristic for quantum mechanics is that whereas in kind of classical physics, the notion is sort of definite things happen, things follow definite trajectories. In quantum mechanics, it's like there are many, many paths that are followed, and we only get to be able to look at sort of the aggregate effect represented in terms of probabilities of all those paths. So kind of the picture here is what there ultimately is in the universe is this network of atoms of space, and there are many different sort of paths of history of those atoms of that network, and that's what kind of leads to physics as we know it. And we're getting sort of more and more detail about how physics as we know it emerges from that very simple underlying structure. But there's one thing that confused me for a long time, which is with this picture, it's like there's a particular rule for updating this graph, this network and so on. Why did our universe get that particular rule and not another one? How do we understand that? And of all the infinitely many possible rules, why do we get this particular one? And what I realized in the end is actually we didn't get a particular one. actually all possible rules are being used. What's happening is, just as there are different paths of history associated with the different applications of a particular rule, so there are different paths of history associated with the application of different rules. And in the end, the way to think about things is that what one has is this object that represents all possible computations. I call it the ruliad. What is the ruliad? It is the entangled limit of all possible computations. The ruliad is a very abstract thing. It's a unique thing. Imagine that you have all possible machines that can do computation, all possible abstract systems that can do computation. You start them all running. They are entangled because two different machines may produce the same result. And that kind of weaves together the different pieces, the structure of the ruliad. So the ruliad is this very abstract thing. You can imagine a notion of rulial space. Sort of as you move around the ruliad, it's as if you are sort of using different kind of computational devices to figure out what will happen in the world. And in a sense, you can even think that different minds are embedded in different places in the ruliad. Different minds have a different way of thinking about what's going to happen in the world, and you can represent that by saying those different minds are at different places in the ruliad. So minds that are very closely aligned will be close together in rulial space. You know, human minds might be all clumped together. You know, cats and dogs might be a bit further away. The weather, with its mind of its own, might be much further away. It's similar to physical space, where we would have a different point of view about kind of what we see out there in the world. If we're standing very close together, we'll say we see the same things. If we're standing far apart, we'll say we see different things. There actually, in our model of physics, there actually are three different kinds of space that turn out to be important. Physical space is the kind we're used to experiencing, what we call branchial space, which is kind of the space of possible histories that's associated with quantum mechanics, and rulial space, which is this much more general thing that is these kind of different points of view about how the universe works. But the ruliad is a completely inevitable, necessary object. Given the idea of computation, there is no choice but to have the ruliad. The ruliad is this limit of all possible computations. It's a unique, inevitable object. So then the question is, well, how do we fit into that? We are observers embedded within the ruliad, made of the same stuff as the ruliad. And the question is, what is our perception of the ruliad given that setup? And what turns out to be crucial is that we are observers of a certain kind. And observers of the kind we are necessarily perceive the ruliad in certain ways. Let me try and give a simpler example first. When we're looking at molecules bouncing around, we can ask the question, what do you perceive about these molecules bouncing around? One feature of molecular processes is they're reversible. If you have a movie of molecules colliding, bouncing off, and so on, you can't tell whether the movie is being run in the forward direction or in reverse. The microscopic collisions all look the same. But yet macroscopically, we know you smash a piece of glass and what you get is something very different. It's a very different thing that you don't go backwards from that. We see the thing smashing. We don't see the thing assembling itself spontaneously from all the fragments. And so that's the phenomenon of irreversibility. That's the phenomenon of law of entropy increase, the second law of thermodynamics, and so on. Why does it happen? Well, it happens actually because of this phenomenon of computational irreducibility. What's happening is the original setup of the system is sort of being run forwards computationally. That computation is effectively encrypting whatever simplicity there was in the initial conditions, in the initial setup of the system. And then the issue is, well, what do we see from that initial setup? In principle, we can take whatever comes out and we can reverse it. But in practice, because we are observers who are computationally bounded, we can't do all that irreducible computation to go and follow through all those steps. We're stuck just saying it looks random to us. If we could do sort of unbounded computation, we could always know this particular elaborate configuration of molecules, that came from this simple initial condition. But because we are computationally bounded, we have to just say it looks random to us, and we believe in the second law of thermodynamics. So the second law of thermodynamics is a consequence of our computational simplicity relative to the computational irreducibility of the underlying processes that are going on. So that's an example of a place where the nature of us as observers determines essentially the laws of physics that we perceive. What we're effectively doing is observers like us kind of are sampling particular pockets of reducibility. I have to say that if everything was purely irreducible, we wouldn't believe there were laws of nature. We would just say everything about the universe is unpredictable. We just have to watch the universe unfold to see what's going to happen. But in fact, we know there are certain pieces of computational reducibility. There are places in which we know there are irregularities in the universe, which we, with our finite minds, are capable of making use of to be able to say that's predictable, that's a law of nature, that's something that allows us to kind of reduce the complexity of the world to something that we can kind of tell a narrative about in our minds. So the question then is not why does the ruliad exist? The ruliad inevitably exists. It's an abstract thing that necessarily exists and is unique. The question that is less obvious is why do we exist? Why are there observers like us embedded within the ruliad? I think that is something which we are within sight of being able to sort of derive scientifically. I mean, one feature of observers like us is that we tend to take huge amounts of input data. You know, we're looking around the room and we're seeing all these pixels of data, and yet we take all that input and we decide we're going to say this word next. We're going to reduce all of that input. We're going to kind of crush it down to at a very slow rate decide what we do next. That seems to be a feature of our brains. It seems to be an essential feature of the thing that we perceive as consciousness, so to speak, that we are getting the sort of single thread of experience that emerges from this sort of crushing down of all of this input. It's something that is different from the rest of the natural world. I mean, in my principle of computational equivalence, it's not that brains are any more computationally sophisticated than random things in the world. You know, people would say, sort of whimsically, the weather has a mind of its own. In the principle of computational equivalence says, actually, yes, all those fluid motions in the atmosphere, they're doing a computation that's just as sophisticated as the computation that happens with all the electrochemistry of neurons and brains. But the issue is that computation that's going on in the weather is very different in character. It's not aligned with the kinds of computations that we do in our brains. And it doesn't have the same feature of taking sort of all of its input data and crushing it down to a single sort of consensus next action. It seems that sort of that feature is something that's very essential to our particular way of perceiving the universe, and it's relevant to what we perceive as the laws of physics. There are other features of this, like, for example, why do we believe in objective reality? You know, each one of us has an internal view of how things work and how we're thinking about things. But we believe that there is an outside world there that everybody sort of more or less agrees how it's set up. And I think what is surprising to me as well, that it seems like the emergence of sort of a reasonable notion of objective reality depends on the fact that there are lots of us. If there was just one of us, we wouldn't have a clear notion of objective reality. It's because we can all extrapolate that our internal perceptions and feelings are similar in other people, and those other people, we're all observing, we're all sort of agreeing about how the universe, how the world works, and that's why we sort of believe in objective reality. It's sort of an interesting feature of that extends to lots of different things. Quantum mechanics, for example, is a place where it's been very confusing to understand why people think definite things happen in quantum mechanics. In quantum mechanics, you're always following these many possible paths of history. Why is it then that people sort of say, yes, a definite thing happened and we agree about what that was? I think the answer to that is it's because, in a sense, we're all very close together in this thing I call branchial space, the space of possible quantum branches. It's similar to physical space. I mean, if you say, what's the night sky like? We'll all say, well, it looks roughly like this. It has these constellations in it and so on. But we all agree about what the night sky looks like because we're all sitting on this one planet. If we were spread throughout the galaxy, we absolutely would not agree what the night sky was like. It's because we're sort of close together, we're many entities close together, that we have certain kinds of perceptions about the way the world works. But you can kind of keep going and try to understand the extent to which, because we are the way we are, then it becomes inevitable that the science that we believe in, the laws of physics that we believe in, must be the way that they are, which is sort of a very surprising sort of metaphysical conclusion that I, for one, did not see coming at all.